section 6.2, permutations and combinations. A permutation of n distinct element is just an ordering of the n element. Just give an order and list all those in order. Permutation. So, here is an example. Actually, yeah, you could see all the necessary informations and the related code and the proofs and visualizations in this web address. And here, the first example tells us there are 6 permutations of 3 elements. If we list all those 6, that can be listed in this way. How? At the first place, at the first position, how many choices we do have? We can choose A or B or C. So we have a freedom of 3 choice. After we fix one, then on the second position, we have 2 letters left. So we can choose 1 out of 2. And at the last position, then only 1 character left. There's 1 choice. So 3 times 2 times 1, 3 times 2 times 1, which is 6. We have 6 choices, 6 cases, which can be listed in this order. Okay? Okay. First, we can have 3 choice, 2 choice, and 1 choices. When n is equal to 4, if you have A, B, C, D, then 4 choices, 3 choice, 2 choice, and 1 choice. So we're going to have 4 factorials. And this is the code for the permutations. Here, if we go there, if we have 3 elements, and then we have, if we have 3 elements, we have these 6 choices, and we have 6 permutations, which are this. Okay. If we have 4, if we have D here, like this, and a range of 4 here, then there should be like this. If we have 4 elements in order, then we're going to have these 24 list. Like this. We have 24 list like this, which is same as 4 factorials. Okay. Anyway, then we now define the number of permutations, which is known as n factorial. There are n factorial permutations of n element. Why? If you use a multiplication principle, then at the first position, we have n choices. On the second position, 1 was already taken, so we have n minus 1 letters left. So we have a choice of n minus 1 for the second position. And then we use the product rule, and we have how many? After two positions were filled out, then we have n minus 2 characters left, so we can choose 1 out of it. So we have n minus 2 choices, and so on. At the end, we have only 1 minus 1 positions were all filled up, and we have 1 position left. And how many characters left? We started with n element, so the very last one was the last 1 choice that we can do at the end. So if you use the multiplication principle or product rule, then all we have to do is just multiply all those choices, which can be written as n factorial. That's the total number of permutations of n element in order. Okay. Okay. Suppose we have 4 tokens. Then think about the number of permutations. How many permutations of the letters A, B, C, D, E, F contain the substring DEF. You have 1, 2, 3, 4, 5, 6 characters, but DEF moves as one group, one subgroups. Okay, then basically what do we have is A, B, C, and DEF. We have 4 characters to be computed. Okay. So, yeah, the permutation, that's the same problem of the permutation of these 4 letters. So how many permutations do we have on these permutations? And we have how many choices? We have 4 choices for the first position, and 3 choices on the second position, 2 choices, and 1 choices. By product rule, it's 4 times 3 times 2 times 1, which is 4 factorial. Is it? Okay. Yeah. If this moves as one block, so 4 permutations. Next, how many permutations of letters A, B, C, D, E, F contains the letter D, E, F together in any order? Yeah. D, E, F moves with one group, but it can be reordered in it. It can be reordered as DFE or EFD or EDF. Okay. Then we have to then how many permutations that this DEF can have? 3 factorials. And how many permutations we can have with these 4 group characters? So 4 factorials. So first we do find 4 factorials, and then we do find the possible number of permutations in this group, which is 3 factorial. By product rule, we have 3 factorial times 4 factorial, which is 6 times 24, which is 144 choices. That's what we have. Okay? Piran. Got it? Okay, good. Next. This is circular permutation. In how many ways can 6 persons be seated around a circular table? In a circular table, 6 persons. How many ways? Simon? Why? Uh-huh. Mm-hmm. So you can just choose anybody to be seated in any place first. Then we have 5 seats left. There are 5 people left. So here you can assign 1 out of 5 first. Then 2 position was filled. And then for the next position, we have 4 persons to be chosen to be seated. So we have 4 choices here. And here we have only 3 persons left to be chosen. Here, 2 persons left. And here, the very last one should be seated. So that will be enough. There's no other cases. Okay? So whole cases in the circular case, because there's no head table is designated. So in any case, we can, the 5 factorials are the choices to be chosen in a circular table. Okay, so in this way, the n persons be seated around the circular table, then n-1 factorial ways are all the cases. Next, R permutation of n distinct element. R permutation of n distinct element. Now we are not thinking about n factorial. We are only choose the R person out of n person group and give an order. List them. These R persons. Here, an R permutation of n distinct element is an ordering of an R element subset of this whole n set. The number of R permutations of a set n distinct element is denoted by P of n R. Okay, we choose R out of n person and then give an order. Okay, then think about P of n R. Here first, simple example. Ordering picks. Example of two permutations of A, B, C. There are how many? We have P of 3, 2. Okay, so 3 times 2, which is 6. And these are the part of those 6 permutations. Okay. Here, if n is equal to R in definition, we obtain an ordering of all n elements. Thus, an n permutation of n element is what we previously called simply a permutation, which was P of n and n, which is an n factorial. The number P of n R of R permutations of an element where R is less than n may be derived from the above. Okay. For example, if n is equal to 6 and R is equal to 3, as is shown in the figure 6.2.3, then first, how many choices do we have on the first position? We have a 6 person, so we have a freedom of choice from 6. 6. For the second position, how many choices do we have? 5 persons left, so we have a choice of 5. For the third position, 2 persons were already taken, so 4 people left, so we can choose one out of those 4. So 6, 5, and 4, isn't it? So 6 times 5 times 4 is equal to P of 6, 3. Here. So P of NR can be counted as this. First position can be filled with any choice from n persons. So second position left the remaining n minus 1, and the third position from remaining n minus 2 persons, and so on until the r's person. R n minus 0, 1, 2, so it should be r minus 1 here. So we have r terms here. What is this? N times n minus 1 times times n minus r plus 1. This is exactly same as n factorial over n minus l factorial, because the n minus r plus 1s are left and all the rest can be cancelled. Okay. So P over nr can be written as n factorial over n minus r factorial. That's it when r is less than or equal to n. This is what you have learned already in middle school or high school. Okay, here. To count the number of ways of order n elements selected from n element set is first you can choose in n ways for the first position, and for the second position we have n minus 1 ways, and etc. And r minus first element has been selected, so the last element should be selected in n minus r plus 1 ways like this, which is same as this. So we write P over nr in terms of factorial in this way. Okay? That's it. So you proved it. So according to the theorem 2.10, the number of 2 permutations of this 3 element subset is what? P of 3 and 2 is 3 times 2 times 1. Okay? Actually 3 times 2, that's enough, which is 6. I think we don't need this one. Okay? And these are the all the possible 6 choices of 2 permutation of this ABC, okay, which I showed you in here, in coding. Anyway, next, in how many ways can select a chairperson and vice chairperson and secretary and treasurer, the 4 positions from a group of 10 persons? how many ways? We have 10 person. We want to choose 4 person in the order because each position has his name. So it's a permutation, choosing 4 person out of 10 in order. So P, this is P of 10 and 4, isn't it? So 10 factorial over 10 minus 4 factorial, which is 10 times, 9 times, 8 times, 7, okay, which is 5040, okay? Like this. Understand? 이경록 어디 있어요? 이해돼요? 10사람 중에서 4명을 뽑는데 그 4명이 다 각각 자기 역할이 있죠? 그러니까 순서를 줘야 되는 문제죠? 그러니까 10명에서 4명을 순서를 주어서 뽑는 문제죠? 그러니까 퍼뮤테이션을 이제 10명에서 4명 뽑는 퍼뮤테이션을 하니까 10 팩토리얼에서 10-4, which is 6 팩토리얼 나눠주면 되는 거지. 오케이? Okay, yeah. This next example talk about Martins and Jovians, and this is skipped. And then we will explain the more general form. Definition 2.15, combination. Choosing R out of the set of n object without order. That is called C of n and R, combinations. Given a set X containing n distinct elements, then any R combination of X is an unordered, this is important. Selection of R elements of X, okay? So we are choosing an R element subset of X without order in it. The number of R combination of a set of n distinct elements is written as C of n and R, or just n choose R, like this. N choose R. And n choose R can be found in this way. N factorial over n minus R factorial times R factorial. Why? Simon? Yes, as you mentioned, this shows the relationship between the combination and the permutation. It's related with this R factorial because of this unordered selection. Here, the number of ways the 5 students can choose 3 of their group to talk with the chairperson is 5 choose 3. The number of 3 elements of 5 elements from 5 elements. Okay. What is it? We're going to choose 3 out of 5 object set. So just choose 5 out of 3. So which is 5 factorial over 5 minus 3 factorial times 3 factorial, which is 10. We have 10 choices like this. We are choosing 3 out of 5 groups. Then we're going to talk about who will be the chair. That's next. Before that, we only have to do just choose 3 first out of 5. Okay, and this also can be found in this way, with this code. Anyway, the next theorem shows in a general form. The number of R combinations of a set n distinct object is n choose R, like this. N choose R. Choose R person out of n object set. N choose R, which is the same as permutation of P and R divided by R factorial, as you seen in the above. And this permutation is same as n times n minus 1 times up to n minus r plus 1. So this is same as n choose R, which is this. This shows everything that we have talked about. Okay? This really shows the relationship between permutation, and combinations. Okay. This figure shows the two permutations of four objects. Here. And also this is another way of showing this n choose R. N choose R can be written in this way as we talked, and also it can be shown in this way if R is in between 0 and n. If the cardinality of X is n, then R permutation of the set X is obtained by first selecting R element from X and arranging them. So choose R out of n first, and then give an order, which is R factorial. That gives us the permutation of n and R. Then n choose R is a permutation of n and R over R factorial, which is this. So this shows what we had before. Since you learned how to find the permutation of n and R. And also, if R is strictly bigger than n, then it is common to define n choose R is equal to 0. If R is bigger than n strictly, then is there a way to choose the 100 object out of 10 objects? There's no way. So in that case, there's no way. So we define it as 0 if R is bigger than n. Next, in how many ways can we select a committee of 3 from a group of 10 distinct persons? Choose 3 out of 10, isn't it? Let's see. Just choose 10 out of 3, which is 10 factorial of 7 factorial times 3 factorial, which is 120. That many. This also can be found with this binomial of 10 choose 3. Here, if you do compute it, then this gives us 120. If you have a 111, 110, and choose 32, then you will have this many choices. If you have this many, then it will be a big number of choices that you have to think. Okay. This command shows the relationship between this combination and the binomial coefficient, which we will learn in the next section. Here, 5 choose 2 times 6 choose 3 is 200. This. In how many ways can we select a committee of 2 women and 3 men from a group of 5 distinct women and 6 distinct men? What do we have to do? We have to choose 2 women from 5 distinct women, isn't it? So choose 2 out of 5. So choose 2 from 5. So C of 5, 2. And next, choose 3 men from 6 distinct men. So choose 3 from 6. Okay, so we have this and this, which is 10 and 20 each. Then, by the multiplication principle, the total number of possible committee can be C of 5 and 2 times C of 6 and 3, which is 10 times 20, which is 200. So we have 200 choices to form a committee which has 2 women and 3 men from the given group of men and women. Next, how many 8-bit string contains exactly 4 ones? How many 8-bit string contains exactly 4 ones? So we have 8-bit string, and we're going to choose ones. How many? 4 times. That is uniquely determined once we tell which bit are 1. This can be done in this way. Okay. We have 8-bit string, and all we have to do is find a position that the 4 ones should be placed. So we just choose the choose 4 positions from 8 possible spots. Okay. So all you have to do is choose 4 ones out of 8 spots. So that's the same as choose 4 out of 8, which is 870. That's it. And example 21 asks us a problem of card games. An ordinary deck of 52 cards consists of 4 suits, which is clubs and diamond and hearts and spades, of 13 denominations each, which include ace and 2, 3, 4, 5 up to 10, and jack and queen and king. So each card has 13 different numbers within 4 different suits. So it forms 52 cards of one deck of cards. So how many unordered 5-card poker hand selected from an ordinary 52 card deck are there? We want to choose 5 cards out of 52. How many choices do we have? All we have to do is just choose 5 out of 52. So choose 5 from 52. Okay? So 52, choose n, choose 5, which is 52 factorial over 52 minus 5 factorial times 5 factorial, which is this. That's the number. Next, how many poker hands contain cards all the same suit? And how many poker hands contain 3 cards of one denomination and 2 cards of a second denomination? You can think better than me because you know how to play those games better than me. Okay, you can read it. Yeah, that's the answers. All you have to do is just to choose each card from a suit and then use a multiplication principle to get your answers. Next, this is an important problem that you will see over and over again while you are studying discrete math. For example 22, how many roots are there from the lower left corner of n by n square grid to the upper right corner if we are restricted to traveling only to the right or upward, like this? If we have a n by n grid like this, if we start from this left bottom to the right top, the rule is you can only go to right and up. So you can go right and up like this, and you can go right and up and right, or you can go right, right, up, up, right, right, and up, up like this. So there are pretty much choices that you can go from here to here. Think about it. One such route is shown in 4x4 grid like this. So each route can be described by a string of n r's, which means you go right, and n u's, which means you go up. Okay? So we can describe by a string, R, U, U, R, R, U, R, U, which shows this. R, U, U, R, R, U, R, U. Okay, this is one root. We're going to find all the possible these strings, eight strings. Okay, so how we can have it? String can be obtained by an order of selecting n positions for the r's among the 2n positions in the string. Okay, this is 4 by 4, so we have 4 plus 4. We have a string. If we have n by n, you have to use n r's and n u's to find a 2n string of r's and u's. Okay, so so after you find the position of r in 2n string, n r's are there, then all you have to do is just fill out the empty spot with the u's. Then we have n u's and n r's are combined. Then if you use those characters, then we can easily go up from the left bottom to the right top, isn't it? So that's the whole idea. Then how many possible ways do we have? We have 2n positions. All we have to is just choose n r's. So choose n out of 2n. That's the whole possible route from here to here. Because after we choose n r's, then all the remaining position will be filled with u's. So, got it, Pirat. Yeah, so right and up. Okay, if you have n r's and n u's, then we can always go there. Only difference is the ordering of those r and u's. So that we just follow those r and u's as is given. Then at the end, we will move r steps from there and r steps from to the up. So we will be ended at this right corner. So this is a whole possible route, the number of whole possible route from here to here. Too easy, isn't it? Very easy. Okay? 웅요빈, understand? Okay? This is a whole total number of way to go from here to here. 2n choose n. Okay. Here, this simple route shows binary sequence has a one-to-one correspondence to the shortest path. Here, the 1, 0, 0, 1, 1, 0, 1. Here, 0 means right and 1 means up. If you make a correspondence like this, then is the ith step is up if ai is equal to 1, and right move if ai is equal to 0. If you make that correspondence, then this gives us right, up, up, right, up. So this binary sequence gives a route from 1 to 0, 0 to 2, 3. This is 5 steps are needed. So corollary of this observation is the number of passes from 0, 0 to AB is always what? A plus B choose A. Let's see. Here in this case, 5 choose 2, isn't it? So 5 choose 3. Basically, they are same. A plus B choose A. Wow, A plus choose B. Okay, with that observation, this is a real problem. This is a motivation for the Catalan number. In n by n square grid, how many roots are there from the lower left corner of n by n square grid to the upper right corner? If we restricted to traveling only to the right or upward. And this is one more restriction. If we are allowed it to touch, but not go above a diagonal line from the lower left corner to the upper right corner, from here to here. We should go from here to here, but shouldn't cross this line. Okay. Difficult problem. But this is a very simple problem, basically. Why? This is a strategy. Counting diagonal avoiding paths. Yeah, we want to find the number of ways to go from here to there, avoiding these conditions, these diagonal lines. Here, so we define a good route, a route that touches but does not go above the diagonal. It touches it but does not go up. So if we go here, go like this. We name it as those are all good routes. Okay. Then we can count. We can count all the number of good routes. We can count it. Next, define a bad route. A route that goes above the diagonal. It goes from here to here, but passes through it somewhere. Okay. We name it as a bad route. Then we can count all the possible number of bad routes. If we add these two cases, then what? Then that's the total number of paths from here to here. Isn't it? That's the total number. We already know this total number, 2 and choose n. We are looking for this number of bad routes. If we can find the number of good routes, then what? If you subtract this number from here, then we have the bad route. And also, if we can find this number of bad routes, then we can find the total number of good routes as well. So we have a choice. Okay? Mm-hmm. So compute the number of bad routes in this figure is n plus 1 times n minus 1 grid from the lower left corner to the upper right corner. So we were asked to find the number of all good routes. Okay, so if we can find the bad route, then we can find the solution. So think about the bad route. Okay, bad route. So here we have a 4x4, here 3x3 grid here. So here we add, we just cut one block here and add it to on the top. So make it n plus 1 times n minus 1 grid. Here's like here 3x3 gives us 4x4 gives us what? 5 times 3. So from 4x4 now we had cut one and we moved this, so we had n plus 1 times n minus 1 grid. Okay. Mm-hmm. In this grid, from the lower left corner to the upper right corner, so if we start from here to here, then in any case, we had to pass through this diagonal line, isn't it? So any route from here to here are what? Bad route on n by n square grid, isn't it? So all we have to, if we find the one-to-one correspondence between this route and the number of bad route, then that's exactly what we were looking for. Okay, that's the whole idea. So we can talk about the number of bad root is equal to the number of n plus 1 times n minus 1 root, which is what? This. Add those, which is 2n, choose a, which is n plus 1. So this is the total number of bad root. This is the total number of start from here to here. Isn't it? Here, when you have discrete. Okay. This is the total number of bad root. Why? We are using a bijection function on the set of bad root and the set of the root on this from here to here. Okay. We can show this function is 1-to and this function is 1-to-1. So there is a 1-to-1 correspondence. So total number of bad root is same as the total number of root from n plus 1 times n minus 1 grid. Okay, since we have only 2 minutes left, so I will allow you to talk about this one-to-one correspondence in Q&A to understand it. Then what do we have? So does the number of good root is equal to this 2n choose n minus number of bad root, which is 2n choose n minus 1. So from this subtract, that gives us 2n factorial over this minus 2n factorial over this. This can be simplified in this way, which gives us 2n factorial over n plus 1 factorial times n plus 1 times n factorial times n factorial, which is the same as 2n choose n over n plus 1. This number is called a Catalan number. This Catalan number has a lot of applications, so you will see the many informations related with this on the web. And from here, you will see if you search it, then you will see a lot of related informations. And this number was defined by Eugene Catalan, Belgian mathematician, while he is considering the solution of problem of dissecting a polygon into triangle by means of non-intersecting diagonals, such as this. Dissecting this and that. I think I have made a website that explains the meaning of Catalan number, and it shows this bisecting method. The number of choices gives a Catalan number, and the number of giving a parenthesis on the list of number also gives the same Catalan number, and the voting Catalan numbers are used, and this is what we defined, the Catalan number. And in binary tree, the Catalan number used that we're going to learn in section 9, chapter 9 or 8, and root tree. These are all the applications of these Catalan numbers. Okay, and we can show this animation. This shows a one-to-one correspondence between the bisecting and the counting, and also this also shows the one-to-one correspondence between this bad root and good root and the binary trees, etc. Anyway, and also pseudo Catalan number is defined in this way, which also has the applications. And I showed you my website that has all those informations. And next thing was a Fibonacci number, and you can find the information on Fibonacci number. These are the websites that my student made it long ago. I think it's 20 years ago. My student made it, and also this This is about Fibonacci number and golden ratio and the Fibonacci number in financial field, so many things. And also, this is also yeah, this is also tells about all the Fibonacci numbers, as you see. Anyway, so, my old student made the information on Fibonacci numbers, so you can take a look. There is a still journal, Fibonacci Quarterly, that shows the new result on the research on Fibonacci numbers. And I added some information, extra information that you may have a chance to read. And Fibonacci numbers has this many interesting equalities that can be used in many mathematics area. And I think this is the last problem. What is wrong with the following argument, which purport to show that there are this number of 2 to this? It should be I will fix it. Yeah, there are this number of 2 to the cube. It's 8-bit strings of length 8, containing at least 5 zeros, and this shows how we fill this 8-bit strings with 0 and 1s, and where we can find the empty spots. And that's the last example that you can take a look and talk in Q&A. Since time's up, we will finish up this chapter, section 6.2, and that's the end of week 9, and we will continue section 6.3, generalized permutations and combinations in week 10. Any questions?